Hi, class. So at this stage of the course, in my mind, I hear the students screaming, "Hold on, I thought this was going to be biology. I did not sign up for a chemistry class." And I totally understand that. But the fact is that to really understand the basis of biology, we must have some idea of the very basic chemistry behind it. Remember in our last chapter, we learned that atoms are some of the smallest components of biological organization. As a side note, I should say that this might not be completely accurate. We can and will actually go smaller, but the atoms are the smallest units that exist on their own. So before we can talk about all this bigger stuff like tissues, organs, body systems, organisms, and eventually the entire life on the earth, we must understand the basic components that make up all of it. Let's talk about matter. When we talk about matter in the field of chemistry, we mean something that is a little different from when your girl or boyfriend tells you that you matter to me. So, what is matter? Is the pen that you might be holding in your hand a matter? How about the computer that you watch this video on? Yes, you got it. Matter is anything that takes up space and has a mass. Matter can take many different forms. It can be solid, like the pen that you are holding, liquid, like juice in a glass, or gas, like the air that you breathe in. Matter is usually composed of different elements. Think about the pen that you are holding. There is likely a mixture of elements in it. Same goes for the air that you are breathing in. Only some of it is oxygen. There are also many other gases. So what really is an element? An element is something that cannot be broken down further into another substance by typical chemical means. There are some exceptions in terms of what we can achieve with advanced technology, so that is why I'm sticking with the term typical means. And if you look, it is this periodic table of elements where we have listed all of the known substances that classify as elements. They are organized based on what we can predict of their chemical behavior, such as reactivity, or as an opposite to that, stability. There are 92 naturally occurring elements that we know of, but this number and consequently the periodic table has been redrafted a few times throughout its history, so I would not be horribly surprised if some further adjustments would be needed somewhere in the future. And four of these elements, carbon, hydrogen, oxygen, and nitrogen, actually make up about 96% of the body weight of a typical organism. So these four are going to be important ones for us to know about. Well, it turns out that elements are made of atoms. So let's look at an atom as an example of it. We will use helium from this periodic table. Atoms are made of smaller parts, nucleus, and a shell. All the stuff at the very center of an atom forms its nucleus, and all the stuff rotating around the nucleus forms its shell or shells. So let's look at the nucleus of a helium atom in a little bit more in detail. In the nucleus you can see protons and neutrons. Protons carry a positive charge, whereas neutrons are neutral in terms of their charge. In case of a helium, there are two of each. Another interesting thing that you will notice is that there are two electrons on its shell. These are negatively charged, so when we add up the positive and negative charges of these subatomic particles, we will see that overall this helium atom is in balance in regards to its charge. It is said to be electrically neutral. Another thing that we will notice with the symbol on the right is that the helium atom has an atomic number of 2, indicated by the little number 2 on the upper left corner of the symbol. This tells us that a helium atom has 2 protons, and if this helium atom is electrically neutral, this means that it will also have 2 electrons. Remember, pluses and minuses canceled each other out, giving an overall neutral electrical charge. Now, some atoms of the same element may have different number of neutrons. These are known as isotopes. They are often chemically unstable and therefore may emit radiation. These radioactive isotopes are useful for us in healthcare field in many different ways. Much of my previous career has been working in the medical imaging field, where we use these as tracers. They are useful because they behave in the same manner as the normal element, but we can follow them with our imaging technology. For example, PET imaging uses this to detect what areas of brain are active during certain tasks. Another example would be using radioactivity to sterilize medical equipment. And yes, before you ask, too much radiation can be bad and lead to cells becoming cancerous. But in a medical field, we are very cautious these days and regulate how much radiation a patient can be exposed to during a certain period of time. The other thing that I want to mention before we wrap up this video is that these electrons on an atom's shell are never in reality still, unlike we show in these diagrams. Instead, electrons are constantly moving around the nucleus and around the shell that they form. There is a limit to how many electrons you can fit in to a single shell. And in fact, atoms can have many shells on top of each other. So the first shell fits a maximum of 2 electrons. If there are more than that, we have to establish a second shell, which can fit a maximum of 8 electrons, and so on, and so on. And what an atom wants to do is to always aim for a state where its outermost shell is full. In case of an atom having only one shell, it would want to have 2 electrons on it. If it has 2 shells, it wants to have 8 electrons on its second shell, and so on. This is when an atom is what you can consider as happy. And if it's not happy, it will try to become happy, either by gaining or losing electrons. This is when atoms start to bond with others. They form molecules. And in our next section, we will talk all about these different kinds of bonds.